Alright, so let's get right into it, ladies and gentlemen. So lesson one, the first thing that I want you to understand is sound. But to understand this, we need to understand what the speed of sound is. So imperial system, it's 767 miles per hour. This is about 343 meters per second. Also, I'm going to stick with the imperial system because it puts us in a good kind of like human relatable type of measurement system. And what we want to do is get the general concept of what's going on, and then you can apply it in a simpler way. So I'm going to actually use feet here, so you can imagine, like, you know, your feet. Even though that's technically not accurate, it's going to give us that general idea that we're looking for. So this is about 1,125 feet per second. So the speed of sound, V, is equal to the frequency times the wavelength. So this thing right over here, this little upside down Y looking thing, this is the lowercase Greek letter called lambda. You're going to see this all the time in any kind of frequency book that's talking about saxophone altissimo or anything like that. This is the lowercase version. The capital looks like this. Right, you put this in your equation and you blow up the universe. Ha ha ha, that's an Einstein joke. And this lowercase f is frequency. We should already be familiar with that, but I'll just go over this thing here called Hertz. So frequency is measured in Hertz, and all Hertz is how many times something is doing something per second. So Hertz is cycles per second, but instead of writing Hz, but you might also see this capital H lowercase z here, then you know that they're talking about frequency. And frequency we're already familiar with, because you tune to a concert A, which is A440. That's our frequency. That's how many cycles per second something is happening in Hertz. And wavelength is exactly what it sounds like. Also, it's how long the length of the wave is. So you multiply these two together and you get the speed of sound, which I just said was 1,125 feet per second. So just think about like 1,125 of these per second. All right, let's move on. All right, so let's take a look at that. Let's look at 440 Hertz, right, which is the frequency. That's your A440 that we tune up to. This is 1,125 feet per second, right? So this is the speed of sound. So how long is a concert A? So if you do the math, it comes out to about 2.5 feet or 2.5 of these. All right, so if we take a look at this equation, ladies and gentlemen, we want to get an idea of about how long A440 is, and we come up with a figure that's about 2.5 feet. Now, I'm going to take the time to explain this, so that way when you want to pursue this further in your own time, you can get it right. Because the way I have it written here is definitely not correct. So in physics, if you ever take physics, I took physics in high school, and day one, first lesson that we learned is you cannot make a measurement more accurate than the device you use to make the measurement. So in this case, this isn't accurate enough. So this is going to give us a 25-foot error. So you do this calculation and it's 1,100 feet per second, which is wrong. All right, flat out. So we actually need more information here. So this would actually come out to about 2.557. All right. So I think it's 2.5568, but I'm just going to round it up to 2.557. So if we have 1,125 feet per second, in 1 second, that's a lot of feet. That's a big distance. So in 1/10 of a second, we wind up with 112.5 feet. So just in 1/10 of a second, something is moved 112 feet away from us. So 100th of a second, it's 11 feet. Still not even the length of a saxophone, the tenor sax. So 1.1 foot, that's a big chunk of a percentage of a tenor saxophone. So technically we would have to take this out even further, but I just want to give you guys a general idea for how this math works. So I'm going to go with this number here, and if you want to do this on your own using this very, very simple equation, you can work this out yourself. Alright, so right now I want to talk to you about a constant. Well, what does that mean, a constant? This number, for our thing as musicians with sound, this number functions like a constant. So the speed of sound functions like a constant. Very similar to the way the speed of light functions like a constant. I mean, the speed of light is a constant, but this functions like one for the process by which we use it. So what does that mean? So that means that no matter what's happening over here, this number has to stay the same. And you get some really cool effects that happen because of that. Just like Einstein, E equals mc squared, you have light, which is the constant. That means that something's staying the same and other stuff is moving to make that number stay the same. So when you think about the speed of light being the same, you get a lot of very interesting effects that a lot of people didn't really realize that was going on. So with the speed of light being the same, everybody measuring the same speed of light, that means as your speed increases, that means that time decreases. In the same way that this speed stays the same, our frequency increases, our wavelength decreases. So playing saxophone and understanding music is very much related to Einstein. So another thing that's related to this brutally simplistic equation is the Heisenberg uncertainty principle, for those of you who are familiar with that. So if you aren't familiar with that, all it says in its most simplistic terms is that the more you know about where something is, the less you know about how it's moving, and vice versa. So just like the more frequency you have, the smaller the wavelength, and vice versa. The more I know about where something is, the less I can say about where it's going and what direction it's traveling and its momentum, how much mass it has. The Heisenberg uncertainty principle, which is related to Schrodinger's cat, which is that cat that can be both dead and alive, is all related to playing saxophone through this basic elementary school equation. Yowzers. Alright, so get ready to have your mind blown, because I'm going to set this up in a beautifully simplistic way that I have right here. So instead of using 1,125, I'm just going to use an arbitrary number, 100, because that's base 10. That's super easy to think about. So if this number is 100, this number is a constant. So whenever we have a constant, that means that this number doesn't change regardless of what's going on over here. So if this number in 1 is 25, we know this number is 4. That's elementary school math. Simple stuff. If this number is 2, this number is 50, this number is 1, this number is 100. So if this number is 200, then this number has got to be 1/2 or 0.5. So let me just write 50 times 2. So I want to show you what happens with frequency and wavelength right here. So the bigger this number is, the smaller this number is. So if we halve this number to 25, then we double this number to 4, which still equals 100, right? So this same kind of thing applies when we're using frequency times wavelength, because it's all based on this brutally simple equation. All right, so you open up your saxophone book and you see something that looks like this, right? This is a physical description of a whole wavelength. Now, this is not what a saxophone wavelength looks like, but this is a much easier way of describing it, and you're going to find this in pretty much every book that talks about wavelengths and all this kind of stuff. So how do we look at this? This length from here to here represents the entire length of the saxophone with all the keys closed, that we call a low B flat. All right, so from here to here, length of the saxophone, low B flat, all the keys closed. So the thing is about a saxophone is that it doesn't produce sound in whole wavelengths. It produces sound in half wavelengths. So think about a tree that produces apples, but this is a special kind of saxophone tree, and it produces half apples. And if you want to make an apple pie, or if you want to make some songs or some sound, then you just have to put these half apples together instead of whole apples.